using p-values. So first thing, a p-value, what it really is, it's the addition of the areas left out here pretty much. So if our z, whatever z value we get, so the area to the left and to the right of that added together will give us the p-value. So that's why we do 2 times the p. So where z is the test statistic. So and you should have used z scores before. So it'll make more sense when we look at some examples. So this is what we're going to do to test the significance using p-values. So we're going to write down a null hypothesis and an alternative hypothesis like we've done before. Test the significance level. So it's 0. So it's always going to be 0.05. So if it's above 0.05 or below 0.05, that determines whether we accept a null or alternative hypothesis. So we're calculating the test statistics. So this is the formula for test statistics you've seen before. So that's what our z-score will be. And then we're going to find the p-value that corresponds to that. So the p-value will just be finding the areas and adding them together. Well, doing 2 times the area that's to the right of it, really. So that's how we're going to do it. So if you look back up here, that area there all together. So to get all of that area, we're just going to find this and times it by 2. So that would be z is greater than or equal to whatever the test statistic is. So it's the probability of that of whatever or z statistic is, and then you do 2 times that. So that's how we're going to get our p-value always. And then the last bit, so if it's greater than 0.05, the result is not significant, so we do not reject. But if it's less than it or equal to it, then it is significant. So therefore, we reject the null hypothesis and take the alternative. So here's an example. So in 36 observations, so the standard deviation is 10. In the past, the distribution has had a mean of 83, but it's believed that the mean has changed. So when the sample was taken, it was found to have a mean of 86.2. So let's just null and our alternative hypothesis first. So in the past, the distribution had a mean of 83%. So therefore, our null hypothesis is that it is 83, or not 80%, just 83. So therefore, the mean is 83. So mu is equal to 83. And then our alternative is that it's not. So now we're going to get our test statistics. So that's just using that formula. So z is equal to x bar minus mu over the standard deviation over root n. So we're just putting all that in. So our sample, so the mean of the sample then, so when the sample was taken, it's found to have a mean of 86.2. So therefore we're just taking 86.2, that's our x bar. So our x bar is always the mean of the sample. The mu is always the mean of the whole thing, or in this case it's the distribution that it had in the past. So 83 all over standard deviation is 10, and our sample, our random sample which was taken, was of 36 observations, so root 36. So you're just putting that into your calculator and you should get 1.92. So that is our test statistic. So if you move on to the next bit then, so calculate the p-value. So if we looked at this on the normal distribution curve, so our 1.92 would be up here. So so we want to get all of this here. So what we're going to get is we're going to get the probability of z being greater than 1.92, and then times that by 2. So that will give us the level of significance then. So so we're going to do 2 times, and then remember, for greater than, you're always going to have to do 1 minus. So it'll be 2 times 1 minus, or probability, z being less than or equal to 1.92. So you're going to look up 1.92 in your z tables, and you get 9726, 0.9726. So it'll be 1 minus, or sorry, so it'll be 2 times 1 minus 0.9726. So 0.0548. So you'll see then that 0.0548, if you convert it to a percentage, it's going to be 5.48%. So that is greater than 5% than our level of significance. So therefore, if you look back up here, so if it's greater than 0.05, it is here. If you look in step 5 there, the result is not significant. So therefore, we do not reject the null hypothesis. So conclusion. So not significant. So we do not reject the null hypothesis. So if you're to think about that on the diagram, then, so that means 1.92. So so like our level of significance is in here for our 95% confidence interval. So that will be for our 95% confidence interval. So it's not outside it. So if it was outside of the confidence interval, so therefore in the black, that would mean that it would be significant. But it's not. So it's within. So our mean here is within the confidence interval. It's close enough to the middle, which is where the mean would be. So next one. So a normal distribution is thought to have a mean of 50. So a random sample of 100 gave a mean of 52.4 and standard deviation of 14.8. So let's do our null and our alternative hypothesis here first. So our null would be that, so looking back up here, so that it is whatever it was in the past, basically. So here it's thought to have a mean of 50, so therefore the mean is 50. And then the mean is not 50. So our test statistic then, so z is equal to x bar. So in our sample then the mean is 52. So the sample of the mean of the sample is 52.4. So we're going to put that for our x bar. Take away mu, which is 50, so that was what our mean always was, all over standard deviation, which is 14.3, over the size 100. That's out of 100. The sample was 100 here. So I get 1.6 here. So that's our z score then. So get our p-value. So we're going to do 2 times the probability that z is greater than 1.68. So that's going to be the same thing as 2 times 1 minus probability that z is less than 1.68. So not significant here again. Yeah, so we get 0.15. So again, our conclusion is that it's significant. So that we fail to reject the null hypothesis. And that's it then, that's all for them examples.